Today we're gonna study chapter 28, part 2, the Hall effect. So we write the Hall effect. Now if we take some slab of copper, okay, here is a rectangle like this, and then this slab of copper has certain length. We put here L, this is L, and then it has certain width. We call this D, this is the width. And this slab of copper has a current traveling down. Let's see, the current is going down like this. So this is the current I, is going down the slab. Now, if the current is coming down this way, it means the electrons are going up like that. So this is, electrons are moving up. The electron goes the opposite of the direction of the current. So the current is coming down. Now, let's take this area here, A, we call it A. So A is equal to D times L, okay? And we introduce a magnetic field. So we have a magnetic field going into the paper. So we put here plus, going like this. So this magnetic field is going into the paper. Now, this B field here will cause the electron to deflect. So we need to know the direction, the way these electrons will go to, the direction, which direction they're going to take. Now, we have to use the right-hand rule. So we have the force, okay, is equal to QV cross B. But since the electron is negative, we have Q is equal to minus E. So the force is equal to minus EV cross B. Okay, so what happened is the velocity of the electron is going up. This is the velocity. We can call it the drift velocity. So the electrons are moving up. So now we need to use the right-hand rule to know the direction of the electron, which way they're going to go after they feel this magnetic field. Now, we use our right hand, and you can see here my fingers, like that. And look at the velocity. The velocity is pointing up. So my fingers will point towards the velocity like that. And look at the B field is going into the board. The B field is going into the board. So I have to flip my hand. So you see, my hand now is flipped. So the velocity is going this way, and the B field is going down. So I rotate my finger. Look at the palm is facing down. The palm of my hand is facing down. My fingers go towards the B field. And look at my thumb. My thumb is going to the left. So you might think the force is going to the left. But we have an electron here. The electron is negative. So this negative sign here is going to flip the thumb this way. So the force is going to the right. So the electron will veer to the right like that. They will veer to the right. Now, this magnetic field made the electron veer to the right. And what's going to happen now, we're going to have a pile up of electrons piling up on this side. Okay? These are the electrons piling up here on this side. But remember, when the electron piles up on this side, they're going to leave their companions, the positive charges, on the left side. Now, something strange is going to happen because these electrons are piling up here on the right side, and the positive charges are piling up on the left side, An electric field is going to be generated. So we have an electric field that's going to go from the positive to the negative like that. So here is an electric field is getting generated going this way. Now, what's so interesting, this force here, this magnetic force that pushes the electron to go to the right, you got another force, electric force, that's act on the electron, and that electric force is pointing to the left. So if you look at here, the electric field is going to the right, and then we have an electron which is negative, and the force is equal to minus E times the electric field. So if the electric field is going to the right, the force is going to go to the left. So this one will go to the left. Okay? Now what's going to happen is these electrons, they keep piling up, and also the positive piling up here. So these two forces, they start to act against each other. Okay, this one and this one. This one is pushing the electron to the right. This force or electric force is pushing the electron to the left. And the pile keeps piling up to the point that these two forces become equal. And when these forces become equal, then you don't have this push anymore because they cancel each other out. And we can state that, we can write this down, we can say minus E VB. I got rid of these vectors because the velocity is perpendicular to the B field. Look at here, the velocity is going up and the B field is going into the paper. They're perpendicular, obviously. And look at here, the force, the electric force. Okay, the electric force is going to the left, and I can just take the magnitude or not, or just get rid of that vector there. And you can see here that the charge of the electron cancels, and then I have the velocity, which is the drift velocity. Remember, I put here D, the drift velocity. So the drift velocity is equal to the electric field divided by the magnetic field. So now we got this nice equation here that we can make use of. What should we do with this equation? We know from previous chapters that the current density J, this is the current density, is equal to N, which is the number of electrons per unit volume, times the charge, okay, and times the drift velocity. We know this. We did it last time, I remember. So I can put here J, which is the current density, times N. This is the number of electrons per meter cube, per volume. And I put here the charge. Let me go up here, sorry. I put here the charge. And then I have V, I put here E over D. Oh, I'm sorry, over B, because this is the magnetic field. I made a mess here. The coronavirus made me do this. No, I'm just joking. So we have, let me write it nicely here. I put N, E, and then I put here capital E, and then I put B. Very good. So now, what should we do with this equation? If you look at J is the current density, we know that J is equal to I, or the current I over the area. This is known. So what I will do, I'll take this J here, and then I plug it there. So I will get I over A, okay, is equal to N E, and then this is the electric field, this is the magnetic field. We need to know what we're looking for. What we're looking for is this N. We need to know this N. How many electrons are per meter cube in the copper that participate in this current? So what do? let's find this n. So I put here, if I go up here, I put n is equal. Let me put here I, and then I put the B field, and then at the bottom I have E, A, and the electric field. Now, you see this A here, this A, that A is this area here. And I told you that the area A is equal to D times L. And here is L, and here is D. This is a rectangle, so this times this is equal to A. So let's, instead of putting A, let's put D times L. So I come down here, there, and I put I, B, and then at the bottom I put E, and instead of putting A, I will put L times D. So I put L and D and E. Okay, this is the equation. Now, you see that DE, this DE here, that's actually the voltage. You remember we have this famous equation which we did in class. V is equal to E times D. This is a famous equation. Okay, the voltage is equal to the electric field times the distance, like in capacitors or in like slab here. So this is actually the voltage, because we created a voltage. We have positive, we have a positive side here, negative, so we have V plus and V minus. So we have a voltage here, and that voltage is this one here. So instead of putting DE, I can put V. So I put I, B over E, L, and then I put V. And this is N. This is N. And here is this famous equation. Okay? Now, this is the current in the slab. This is the B field that we introduced. This is the charge of the electron, the magnitude. This is L, the length of the slab. This is V, the difference of potential between the two sides that got generated by having the electron go into one side and the the positive charge going to the other side. Now, what can we do with this equation? Why is this equation important? Look, this current we can measure. We can measure, just use an ammeter and measure the current. The B field, we're the one who introduced it. Actually, this Hall actually, he was a graduate student, 24 years old graduate student at Johns Hopkins. I think his name was Edwin Hall. And he discovered this just by, he wasn't looking, he was doing some other research, and this thing came up. He noticed that this voltage gets created between the two. This voltage gets created, noticed that it's happening. I said, hey, what's going on? Why do we have a voltage here? And then later on he figured this is what's happening. An electric force gets generated as the electron moves in a magnetic field. You have another electric force that gets generated between the two sides of the plates. So now, why is this formula is important? Let's see why. This L, we know. This length of the slab, we know. The voltage we measure with the voltmeter. This E is known, we know. B, we know. The current, we know. So we will know N. But what is N? Is the number of electron per meter cube that in the copper. So you take off the copper, you put the zinc, and you find N. You take off the zinc, you put iron, you find N. So this is a good experiment, tells you how many electrons participate in some metal to generate a current. If you put in some magnetic field or some voltage or so you can actually know which metal can give you free electron for motion. So this is an important equation. That's why this is a part of chapter 28, call it part 2, the Hall effect. Okay? See you.